Good morning. I hope you are well. Let us do some revision on our machines. The first example that we're going to look at is the results were obtained on a 6600 volt alternator. If you look at the graph values there, we'll have to now draw a graph of that. The first thing that we do we choose our scales. Now normally you would choose a scale so that it fits the page. In this instance, I have chosen 1 centimeter is equal to 500 volts on the volt scale, and on the field scale I've chosen 20 millimeters is 10 amps. Now we can plot all these values on the graph. There you can see the first point is 3100 at 16 amps, and then 4900 at 25 amps, and 6600 at 37.5, and 7500 against 50. And then for the short circuit, a field current of 20 amp was necessary to circulate full load current. Now the full load current, as we can see on the graph, was 37.5 amps for the field. Therefore, we need one point on this graph, which is 20, and on this side 37.5. Now for this scale of the short circuit, I chose 20 amp for 1 centimeter. So we just join that point and the origin and draw a straight line through it. Okay. Now, the question asks us to calculate the power factor of 0.8 lagging the voltage regulation using the Ampere turn method and then the synchronous impedance method, where we can ignore the resistance and the leakage reactance. Now, the field current that we are going to need is I short circuit at an angle 0 minus I open circuit at an angle minus 90 plus or minus 5. So that gives us 20 angle 0 minus 37.5 at an angle of minus 126.87. That gives us 52.02 at an angle of 35. We're not much interested in the angle. So from the graph, we go back on the graph, and at 52, we find that the open circuit voltage is 7,600 volts. And therefore, the voltage regulation is 7,600 minus 6,600 divided by 6,600, which gives us 15.15%. Now, in this instance, you could have used the line voltages as it is or convert it to phase voltage. Doesn't really matter. Now, the synchronous impedance method, let's say the voltage 6,600 is 100%, and also the full load current 37.5 is also 100%. The full load field current is 20 amps, which is also given as 100%. So if we apply 37.5 amps on the short circuit, then the short circuit current should be 100 times 37.5 divided by 20, which gives us a value of 187.5%. So ZS is V open circuit over I short circuit, which is then 100% divided by 187.5, which gives us 53.3%. And now we can determine the induced EMF, which is 1 angle 0 plus 1 angle minus 36.87 times 0.533 at an angle of 90. That gives us 1.387 at an angle of 17.8. Now the voltage regulation is 1.387 minus 1. That gives us 38.7%. Hopefully you understand this. Next thing that we are going to have a look at a 2200 volt, 50 hertz, 3-phase star connected alternator has an effective resistance of 0.5 ohm per phase. A field current of 30 amp produces the full load current of 200 amps on short circuit and a line-to-line EMF of 1100 on open circuit. We must compute the load angle on full load for a lagging power factor of 0.8 and the short circuit ratio. Now the impedance is the voltage open circuit over short circuit current at the same excitation. So it is set there 1100 volts on open circuit and 200 amps. So that gives us 3.175 ohm. Now XS is the square root of ZS squared minus R squared. So that will be 0.3175 squared minus 0.5 squared, which gives us 3.136 ohms. The impedance angle is R cos of R over Z. That gives us 80.94 degrees. Now we can calculate the induced EMF. That is 1270 plus 200 at an angle of minus 36.87 times 3.17 at an angle of 80.94. That gives us 1782.012 at an angle of 14.35. So our load angle is 14.35 degrees, and the short circuit ratio is 1 over X, and X we calculated, 3.136, and therefore short circuit ratio is 0.319. Now let's look at the power flow diagram for an alternator. We have the output of the prime mover, which is the input, and also it supplies mechanical power to the exciter. Then we get exciter losses and the excitation DC to the field of the alternator. That leaves us with a mechanical power supplied to the alternator. Then we have mechanical losses, which is friction, windage, hysteresis, and eddy current. Then the next stage is the mechanical power converted to electrical power. And there we have the electrical power lost in the armature circuit, which is normally 3R squared, I squared R. And that gives us the electrical output power. Now let us look at load sharing between alternators. There you can see that we have the two alternators in parallel. They're supplying a load. So V1 is E1 minus I1 ZS1, and terminal voltage again is E2 minus I2 ZS2. Also that V is equal to I load times ZS. which is equal to 1 plus I1 plus I2 times the load impedance. And therefore, we can say that I1 is equal to E1 minus V divided by ZS, and I2 is equal to E2 minus V over ZS2. And therefore, I1 plus I2 is equal to E1 minus V over ZS1 plus E2 minus V over ZS2, and that is all equal to V over Z. Then if we manipulate the formula, we get that V is E1 over ZS1 plus E2 over ZS2 divided by the sum of the inverse of ZS1, ZS2, and Z. Now let's look at an example. Two single-phase alternators operating parallel on a load of Z ohms. The EMFs are E1 and E2 with Z1 and Z2, their impedances. Deduce the terminal voltage in terms of these EMFs and the admittances. Now, if we look at that, you can say 1 over Z1 is Y1. Therefore, we get V is equal to E1 Y1 plus E2 Y2 divided by Y1 plus Y2 plus Y load. Now, we must determine the terminal voltage and kilowatt of each machine. If E1 is 100 and E2 is 110 volt, Z load is 3 plus J4, Z1 is equal to Z2, which is 2 plus J1. Now we stick it in the formula, and we get a voltage of 96.071 at an angle of minus 2.3. I1 now is E1 minus V times Y1. That gives us a value of 5.458 angle minus 34.67, and I2 is E2 minus V times Y2. That gives us a value of 14.818 angle minus 63.23. Then the complex power S is 1 is equal to V times I1, the conjugate of V. That gives us 443 minus J 2.807 voltage VARs. And S2 is 692 minus J1244.2. The next example. A 3 MVA 6-pole alternator runs at 1000 revs per minute on a 3.3 kilovolt bus bar. The synchronous reactance is 25%. We have to compute the synchronizing power and torque per mechanical degree of displacement when the supply full load at a lagging power factor of 0.8. First of all, we calculate the full load current, which is S divided by square root 3V line. That gives us 52.5 amps. Then the induced EMF, because the synchronous reactance is given in per unit or percentage, we have to work in per unit or percentage. Now, per unit then will be E angle delta is 1 angle naught plus 1 angle minus 36.87 plus 0.25 times 0.25 angle 90. That gives us a value of 1.17 at an angle of 9.87. And if we convert that to actual values, we get 2,224 volts. So the synchronizing power is 3 p pi over 180 times EV over X sine 90 plus delta. Now that becomes 3 pi over 180 times 1.167 divided by 0.25 cos of 9.87. Now that 3 falls away because we are working in per unit. And that gives us a value of 0.2408 per unit. Converted to real kilowatt, we get 722.488. Then the synchronizing torque will be 60 times the synchronizing power divided by 2 pi ns. That gives us a value of 6898 Newton meter. The next example is a 5 MVA 10 kilovolt 1500 revs per minute 50 Hz alternator that runs in synchronism with the system. Its reactance is 20%. Compute at no load and then at full load, power factor lagging the synchronizing power per mechanical degree of phase displacement. So the synchronizing torque if the mechanical displacement is 0.5 degrees. I full load is S divided by square root 3, gives us 288.7 amps. Delta is P pi over 180. Simplify it, gives us pi over 90. Induced EMF is 1 angle 0 plus 1 angle minus 36.87 times 0.2 angle 90. That gives us a value of 1.1314 at an angle of 8 degrees. Now at no load, E is equal to V, so therefore the synchronizing power is pi divided by 90 times 1 squared divided by 0.2, which gives us 0.17 per unit. Convert that back to actual value, we get 872.778 kilowatt. Then the synchronizing power, torque, is 60 times P divided by 2 pi ns. That gives us a value of 5.556 kilonewton per meter. Now the synchronizing torque for 0.5 mechanical degrees will be 0.5 times 556 is 2777.8 Newton meters. Now delta is that angle there is 2 times 1 because it's per mechanical degree, so therefore it becomes 2 degrees. And the synchronizing EMF is 2E sine delta over 2, which gives us a value of 7.916 at an angle, 7.916 times 10 to the minus 2 per unit. Okay, then we can go on to the next example. Two AC alternators are running in parallel to supply a lighting load of 2000 kilowatt and a motor load of 4000 kilowatt at a power factor of 0.8 lagging. One machine is loaded to 2400 kilowatt at a power factor of 0.95 lagging. Compute the output and the power factor of the second machine. So the total kVA is the lighting load plus the motor load, that is 2000 divided by 2000 angle 0, plus, now we convert the 4000 kilowatt to kVA, and that will be 4000 divided by 0.8, which gives us 5000 at an angle of minus 36.78. And therefore, the total kVAR is 6708.202 at an angle of minus 26.7. Therefore, machine 2 supplies the difference between total kVA minus the kVA of the first machine, which is 2526.316 at an angle of minus 18.2. That is 2400 divided by 0.95 at that angle. That gives us 224.78 angle minus 31.6, and therefore the power factor is the cosine of 31.6, which is 0.8521 lagging. The next example, basically the same. Two alternators operate in parallel to supply the following loads: a lighting load of 500 kilowatt and 1000 kilowatt at a 0.9 power factor lagging, and 500 kilowatt at 0.9 leading, and 800 kilowatt of 0.8 lagging. One alternator is supplying 1500 kilowatt at 0.95 lagging. Compute the load on the other machine. So the total kVA is the sum of all the separate ones. So that's 500 times 10 to the power of 3 plus 1111,11 at an angle of minus 25.84 plus 515.98 at an angle 25.84 plus 1000 angle minus 36.87. That gives us a value of 289.4.856 times 10 to the power of 3 angle minus 17.27 kVA. So the load of machine 1 is 1578.947 at an angle of minus 18.2. And the difference between the two kVAs is 1316.366 angle minus 16.15. And the power factor is the cosine of 16.15, which gives us a value of 0.961. Now let's look at a power flow diagram for a synchronous motor. We've got the AC power input to the stator, then we've got the armature copper loss. Then we are left with the mechanical power developed in the armature. We get the losses, iron, excitation, friction, and windage loss, and that gives us a net output, or the useful output power. Example, a star-connected 187 kVA, 2300 volt, 47 amp, 50 hertz, 187.5 revs per minute synchronous motor has an impedance of 1.5 plus J20 ohms per phase. Computer developed power when operating at rated current and 0.8 power factor lagging. So first of all that we have to calculate is the induced EMF, which is V minus IA ZS beta plus or minus phi. That is 1327 angle 0 minus 47 at an angle of 36.87 lagging times the impedance, which is 1.5 plus J20. That gives us a value of 1002.115 at an angle minus 45.1. Now we can determine the developed power, which is E times V over Z cos beta minus delta minus E over Z cos beta. If we substitute that in our equation, we get 139.770 kilowatt. Or we can say that the input power is 3 square root 3 V line I line cos phi, which is 149,787.754 watts. And if we subtract the copper loss, which is 3I squared R, we get the developed power is 139,847. Again, if we look at the phasor diagram, it is V, and then IR is the volt drop across the resistor in the armature, and IX is perpendicular to the current that causes it. And remember, civil, in an inductor, the voltage leads the current. And that leaves us with E. It is very important that you understand the phasor diagrams of these machines, otherwise you are going to struggle forever. Now, example 3, a 75 kilowatt, 400 volt star-connected synchronous motor has an impedance of 0.04 plus J0.4 ohms per phase. Computed for full load at a power factor of 0.8 leading with an efficiency of 92.5%, the induced EMF and the gross mechanical power developed. So the input is the output divided by the efficiency, which gives us 81.081 kilowatt. Then the motor current will be P divided by square root 3 V line cos phi, which is 146.3. We calculate the induced EMF. It is V minus IMZ beta plus or minus phi. That gives us a value of 266.231 at an angle of minus 10.9. And the mechanical power is 81.081 kilowatt minus 3 times 146.3 squared times 0.04. That gives us 78.513. Now again, if you look at the phasor diagram, remember for an alternator, the leading power factor is in that direction. And for a motor, because the current is reversed, it is downwards like that. So then we get V plus IR plus IX. And that gives us the induced EMF. Okay, this is the end of this chapter.